Cryptography has been around for thousands of years, but throughout that history, the form it took was symmetric. That meant that it relied on the sender and receiver sharing a secret key that wasn't known to the adversary. The question of how you might arrive at that key led in the 1970s to a revolution, which was the invention of what's now called public key or asymmetric cryptography. That required or exploited a set of techniques arising from the classical mathematical domain of number theory, thereby creating a bridge between number theory and new applications. So in order to study public key cryptography, we're going to take a brief tour of number theory with an emphasis different from the one usually in a mathematics class, not only on the mathematical basis, but on computational aspects, which means we're going to be worried about algorithms and the cost of computing those algorithms. So the motivating question which led Diffie and Hellman to invent public key cryptography was to arrive at a shared symmetric key that could be used for symmetric cryptography. So assume Alice and Bob want such a key, but they're at opposite ends of an insecure channel, and they want to obtain this key simply by sending each other messages according to some prescribed protocol. Now, possibly they do share some information, but that's public. It's known to the adversary as well, and everything they communicate will be visible to the adversary. Is it possible in this regime, nonetheless, to interact and after a few rounds arrive at a key that Alice and Bob know, but the adversary doesn't? So to be more precise about what we mean by interact, Alice could make choices of things at random. She could then obtain functions of those things and transmit those. And Bob could do likewise. He's allowed random choices and computation of simple functions on those choices, and then communication. At the end of all of this, Alice applies some function, a public function prescribed by the protocol, to her random choices and whatever she got from Bob. Bob likewise to his random choices and whatever he got from Alice. This results in keys for each of them, and the desired properties are that the keys are the same. And furthermore, if you give the adversary the computation here, meaning whatever was communicated, it's not able to compute this common key. And the problem here is called secret key exchange. So we're asking, can you do it? Okay, so we've seen a whole bunch of cryptography techniques so far. We've seen symmetric encryption, block ciphers, hash functions, PRFs, and all that. So we have a lot that we could bring to bear on this problem. So we could give it a try. Can you build a secret key exchange protocol? Perhaps we would have Alice pick a key and then, well, she can't send it to Bob in the clear because then the adversary would see it. So maybe she has to encrypt it. But then the question is, encrypted under what? She has nothing to encrypt it under that Bob has in order to decrypt it. And so we start seeing it's not so easy. But it's more than not easy. It turns out that historically no solution was found, to the point where people thought there just doesn't exist a way to do this. But in the late 70s, Diffie and Hellman found a solution. And that was the birth of public key cryptography. There's a video here, if you're interested, that kind of gives a layman's view of how it works using analogies with mixing of colors. But we'll go on to the math of it. Now, what's kind of remarkable, perhaps, is that this rather difficult problem at this point has a solution which I can roughly show you in one slide with not much introduction, even though it will take us the rest of this chapter to really understand all that's going on here, it's still possible to interpret the protocol. So it assumes that a large prime number is public and also another number G called a generator mod P. The simplest thing to do at this point is just assume G is 2. How large a prime? Many thousands of bits long, so really rather big. Alice then will pick a random number in this range. This means a number between 0 and p minus 2. She will then multiply G by itself x times, raise G to the power x, but take the result mod P and transmit that to Bob. And Bob simply does likewise, picks a random number y in that range, raises G to the power y, takes the remainder mod P and sends y over. And now comes the arithmetic magic. So Alice computes the number Bob sent, raised to the power her little secret x here. Bob correspondingly takes the number Alice sent, big X, and raises it to the little y, which is his secret here. But we claim they get the same thing, and those two things are both equal to G to the power little x times little y. You can see that quite easily, because you can write this either as G to the little x, the whole thing to the little y, which is big X to the little y, or G to the little y to the little x, which is big Y to the little x. And so we've shown that the two keys are the same and are equal to this mod P. Now, what about the adversary? Well, it has neither of the little things. It doesn't have the little x or little y, so it's faced with the problem of taking G to the power little x, G to the power little y, and getting this from them. And it turns out that we do not know to date any efficient way to solve that problem. And thereby we believe that this provides the desired security. Now, as we approach understanding this better to the point where we can implement it and understand the security of it, we have a whole bunch of questions to answer. For example, we need a large prime, but how do we find that? And how large is large enough? We said G was a generator mod P. What does that mean? And once we know what it means, how are we going to find a number like that? How is Alice going to quickly raise G to the power little x mod P? That's an algorithmic operation which in principle may not be simple to perform, similarly for Bob. And finally, of course, what sort of evidence can we give in favor of the security claim that this function here is actually hard to compute for the adversary? And so to do this, we'll forget about Diffie-Hellman secret key exchange for a while and just study computational number theory. And we'll find when we come back at the end of this chapter, we will have answers to these questions. So we start with a whole bunch of little notation, nothing difficult going on. Z will be the set of integers, both positive and negative, n the set of natural numbers, so 0, 1 onwards, and z plus the set of positive integers. If we have two integers, either positive or negative, their GCD is the largest common divisor, namely the largest number that divides both of them. The divisor itself here does have to be a positive integer. For example, the greatest common divisor of 30 and 70 is 10 because 10 divides 30, 10 divides 70, and nothing larger than 10 divides both 30 and 70. When we are doing cryptography, we're usually working over finite sets, not the type from the last slide. Some finite sets of interest are Z mod n, the set of all numbers between 0 and n minus 1. Intuitively think of them as the possible remainders you get on division of numbers by n. A subset of this is Zn star. It says, look at all these points and confine attention to those whose greatest common divisor with n is 1. In other words, they and n should have no non-trivial common divisor. So that gives you a certain selection from these numbers. Clearly, this set has size n from 0 through n minus 1, the n points. How many points does this set have? It's not that clear, but that number is interesting, and mathematicians call it the totient function or Euler-Phi function, and phi of n is defined to be the size of this set. Remember, bars around a finite set returns its size. For example, if n is 12, well, z12 is just everything from 0 to 11. What is z star 12? Take all these numbers, throw away anything with a common divisor with 12, meaning throw away anything that has a factor of 3 or 2 in it. What will that leave us with? Well, 0 is gone because 12 divides 0. 1 is fine. 2 divides 12, not okay. So does 3 and 4. 5 and 12 have no common divisor, so 5 is okay, and so forth. What is phi of 12? The size of this set, so it would be 4. The integer division function is the one that, given an integer a and another integer n, performs division and returns both the quotient and the remainder. So you write a as the quotient times the number you're dividing by plus r. The definition of remainder is that it's a non-negative number strictly smaller than what you're dividing by. So one of the outcomes of this is the mod function, because a mod n is just the remainder from integer division. For example, if you run integer division on 17 and 3, well, 17 is 15 plus 2, which is 5 times 3 plus 2. So you would expect to get 5 as the quotient and 2 as the remainder. In particular, 17 mod 3 is recovered as 2. A piece of notation here is that often we're interested only in what happens to numbers modulo some fixed number n. And if we have two large integers, we write that they're equivalent mod n if the remainders mod n are the same. For example, 17 and 14 are equivalent mod 3 because 17 mod 3 is 2 and 14 mod 3 is also 2. Now, a lot of the structures useful for cryptography in number theory are what mathematicians call groups. And you've hopefully encountered these before, certainly in any algebra course in an undergraduate math program, you will have encountered them. So we'll briefly review what groups are and give examples of the ones of most interest to us. So you start with a non-empty set G, and then you have a binary operation on it. A binary operation is simply something which takes 2 points in the group and returns an output. More formally, it's a function from G cross G to some range. We denote the result of the binary operation on A and B by A dot B, connoting multiplication. But it is to be remembered that this is simply an abstract operation. It can be anything, and the group itself will tell you what it's supposed to be. As an example, let G be the group of integers mod 12 and relatively prime to 12, Z star 12 that we just saw. We could let dot be not plain multiplication, but multiplication modulo 12. So for any 2 points in here, A dot B says form the normal integer product, but retain only the remainder on division of 12 by 12. Now, G is a group if it has 4 properties called closure, associativity, identity, and inverse, and we'll present them next briefly. And one of the facts that we will need and use as we go forward, and also use as an example as we go along, is that things of this form are groups under this operation. More generally, if n is a positive integer, and we consider Zn star, with the operation being multiplication mod n, it satisfies all these 4 properties and is a group. Okay, so what are these properties? Closure simply says that if you operate on 2 points in the group with your operation, the result is also back in the group. And Is this maybe easiest to understand by, as often with group properties, by non-examples, things that fail. For example, suppose G is Z mod 12 and our operation is normal integer multiplication. Well, it doesn't have closure. Why is that? 7 is in the group, so is 5, but the product is 35, which is not in the set. I shouldn't say group because it's not a group. However, if we look at Zn star with multiplication mod n as the operation, it does satisfy closure. Now note that this claim is somewhat non-trivial mathematically. Why? Because what it's saying is that if A and B are in Zn star, we know that their GCDs with n are 1. And what the fact is saying is that if you take the product of those numbers mod n, the GCD with n continues to be 1. And that needs a little math, which we won't do here, to verify, but in a number theory or algebra course, things like that are often done. As an example, you can check in Z star 12, if you take any two numbers in there, like 5 and 7, and multiply them, you get 35, but we have to reduce mod 12, that leaves 11. But 11 is back in this set. In other words, what closure is saying is, if I take 2 points in this set and multiply them mod 11, I will never, for example, get an answer of 8. Associativity simply says that if you have to multiply or operate on lots of stuff, you can put parentheses where you want. So 8 times B done first and then C is the same as first doing the B and C and then the A. So again, if you are in our Zn star set with multiplication mod n as your operation, it turns out you have associativity. Right? And what does that mean over here? For example, if I want to compute 5 times 7 times 11 mod 12, I can first do 5 times 7 and reduce it mod 12. That will give me 35 mod 12, which is 11, and then multiply by 11. I get 11 times 11, 121 mod 12, which is 1. Alternatively, I could first multiply 7 and 11 mod 12, and that'll give me 77 mod 12, which is 5. And then bring in the 5 and multiply by that. I get 5 times 5 is 25 mod 12, which is 1. And associativity is just saying you get the same thing either way. Again, it's interesting to think about this through non-examples. Can you give an example of a set G and a natural operation on it? It should satisfy closure, but it should fail associativity. And this little exercise, I think, will help you understand associativity more and also appreciate that it's not a triviality. It doesn't always happen. When we consider multiplication, we know that under normal multiplication of numbers, if you multiply anything by 1, you leave the anything unchanged. So a group is asking that there is an element called the identity element which plays the same role. If I operate with the group operation on some A and that identity element, I just get back A, and that's true regardless of the order in which things are done. So although again it's written with a notation that connotes multiplication, it needn't be. For example, if the operation is addition, maybe this 1 is numerically actually a 0. This is just an abstraction over here. If we are in our example where the group is Zn star with multiplication mod n, then the identity element actually is the integer 1, clearly, because A times 1 mod n is 1 times A mod n, which is A. The final property of a group is effectively that division is possible. And the way that's captured is by saying that there exists for any A in the group a unique number B that intuitively plays the role of 1 over A. But 1 over A doesn't make sense in a group, so you define the properties of B through what 1 over A would do. And what that means is if I operate on A and B, I get back the identity element. So in that sense, B is an inverse of A, and it works in either order. When the group is understood, we write A inverse like this for this inverse. Now, let's say we go to our example again, Zn star with multiplication mod n. What does it say in this case? This being a group says that whenever I have a point in Zn star, there's another point in Zn star and it's unique, such that when I multiply A and B mod n, I get back the identity element, which is 1. Now this is not necessarily obvious. Remember, we have no fractions here. This B is an integer. But when I multiply them and take the remainder mod n, I should get back a 1. So why does this exist? Well, that again, we'll leave that to a math class and we'll believe it here. But for example, suppose you needed to find the inverse of 5 mod 12. Since 5 belongs to Z star 12, this fact says it has an inverse. Can we verify that? Well, it should be a point B in Z star 12 such that 5B mod 12 is 1. How do we find it? Well, at the moment we don't have anything clever, but we can try different points in Zn star. And you see that the resulting answer is 5. Why is that? 5 times 5 is 25, and 25 mod 12 is 1. So to summarize now, we have given a definition of a group, and groups can be very different. There are many, many different examples of all kinds, but the ones of interest to us, the one we worked with as a running example, was the group of integers mod n and relatively prime to n under multiplication. So Zn star under multiplication mod n. Another simple example of a group that keeps coming up is Zn without the star under addition mod n. So here the operation on A and B is you sum A and B as integers and take the result mod n. And here the identity element is 0, inverse is done by subtraction, and so forth. These exercises are to show you how groups can look quite different as well. This is a group formed out of string operations, XOR. And this is an example of an operation that doesn't yield a group, so you can see how to disprove. Now, it's fun to play around with numbers as we grow to understand how group properties allow us to manipulate them and give us more insight into them. And one of the ways you can see this is just little shortcuts or ways to perform computations that would look implausible to do by hand if you didn't know some number theory. So as a little example, suppose I needed to compute this product of 4 numbers mod 21. The natural way to do it would be first compute the product. So of all those 4, okay, let's try 8 times 5 is 40, times 10 times 16, so 400 times 16. That may take a little bit, but it comes out to 6400. And now we have to do the mod. And that takes some work. Maybe we need a calculator, but it turns out to be 16. So here's the fast way. We notice that group properties like associativity allow us to do computations as we go along. So once I've multiplied 5 and 8 here, I don't need to leave it as 40. I can already reduce mod 21. And so I'm left with 19. And that goes on. I now multiply 19 by 10 to get 190. But rather than continuing with that, I already reduce mod 21. And 189 is a multiple of 21, so the mod value is a 1. Now I multiply 1 by 16 mod 21 and reduce mod 21. There's nothing to do with that, and you get 16. So in this way, quite long chains can be quite simply computed. Now when we come to encryption, we'll see that the central operation is raising points in groups to integer powers. That's called exponentiation, so let's look at that a bit. we have here our abstract group and a point A in it, and I'll define A to the power 0 to be the identity element. If you're working in Zn star, that would just be the number 1. And for a number n which is more than 1, raising A to the power n is the obvious thing. You multiply A by itself n times, again with the understanding that this is a group operation, which is not necessarily multiplication, but often for us multiplication modulo some other number. It's good to keep the types of objects apart here. The exponent n is a normal integer, just a number. A is an abstract group element. It might be an integer in certain groups, but it doesn't have to be for these definitions. Now I want to think of what happens when I raise the group element to the negative n, but this is not something I can just say, oh, its value is something, because we haven't yet even defined what it could possibly mean. I only know what raising A to non-negative powers means. So I define A to the negative n to mean take the inverse of A in the group and multiply that by itself n times. Now, this equation looks like a tautology. It isn't. It's actually saying quite a few things, because this is a group operation of returning the inverse. And through that, we are defining A to the power negative n. However, the nice thing is that once we made all these definitions, everything works like it should. Like it should means you can manipulate exponents just as you would with normal arithmetic. For example, A to the power I plus j would be A to the power I times A to the power j. A to the power I times j is A to the power I raised to the j, which is then this. Now again, these things look like tautologies, but you would actually need to prove them and understand that there's quite a bit going on. The exponents are always integers. They can actually be positive or negative. A is a group element. This is saying raise A to the sum of these two numbers is the same as raising A to the I and operating on A to the j. And this is A to the I operated on itself j times and so forth. A to the negative I you can compute either by raising A to the I and taking the inverse in the group, or first taking the inverse and then raising to the I. With this done, we will be free to kind of use exponents and manipulate them in the usual way. Now, we are mostly interested in finite groups, and one number of importance relative to them is their order, which is the number of points in the group. So, for example, consider the group Z star 21. What is its order? Well, to know that, to compute that, we have to figure out what the group actually is. So let's write down what Z star 21 comes to. How do we get that? We take all numbers between 1 and 20 and throw away anything that has a common divisor with 21. So we throw away all multiples of 3 or 7. And here's what we're left with. Now, count how many things there are in here, and it turns out there are 12. So the order of Z star 21 is 12. There's a very basic fact about orders, which is something you learn in the very first few weeks of a algebra class, which is that take any point in a group, let m be the integer that's the order of the group. I can raise A to the power m in the group. And the fact says that no matter what A is, I will always get back the identity element. So operating on A itself, m times will always return the identity element. It's an interesting proof, again, not something we want to do here, but we could check it out. For example, in this group, the order is 12. The fact should say if I take anything in here, for example, 5, and raise it to the power 12, I should get 1. You can check it. It's also nice at this point to utilize some of our shortcutting techniques. Normally, raising 5 to the 12 mod 21 would be a call for a calculator or something, but we won't do it that way. We'll write 12 as 3 times 4. So now this is 5 cubed, which we can first reduce mod 21. So 5 squared is 25. 25 mod 21 is 4. And 4 times 5 is 20. So we get 20 to the power 4. Another little trick. 20 is the same as negative 1 mod 21. And it's easy to raise negative 1 to the 4. So it worked. Take another thing, say 8. Raise 8 to the power 12. Again, play around a bit. Write it as 8 to the power 2 to the power 6. 8 squared is 64. And 63 is a multiple of 21. So mod 21, it's a 1. And so you get back a 1. Okay. Now, just for a little reminder, there are lots of numbers floating around here, and you need to keep track of them. The group is modulo 21. Multiplication happens modulo 21. So in all of this, we are doing multiplications modulo 21. 12, the order of the group, is a different number, and it's the number appearing in the exponent. There's an extension of that fact that helps us compute high powers of group elements. So again, let G be a group and M its order and A some point in the group. Say now I want to raise A to some power I, and think of I as a big number. What this says is I only care about the value of I mod M. I can take I and divide it by M and take the remainder, and I only need to raise A to that power, and it'll get back the same thing. Now, for once, we'll actually give a proof. Why is that? It's one line and it's kind of revealing. So let's take the division of I by M, integer division, and that'll give a quotient and remainder. So that means I've written the power to which I want to raise A as the group order times some quotient plus a remainder. And by definition, the remainder is this thing mod M. Now look what happens when I raise A to the I. Of course, it's A to the M cubed plus R, which by our usual rewriting can be put like this. But A to the power M by the fact is just 1. So this is 1 to the q, which is 1, and goes away. And we're left with A to the R, and R is I mod M, so that's the claim of the theorem. So as an example of how you might use this, suppose I ask you to compute 5 to the power 74 mod 21. Now, if you don't know anything about group theory or these results, you would look at this and immediately reach for a calculator or type it into Google or so forth, because they look like dauntingly large numbers. Raising 5 to the 74 looks like a lot of work and would result in a big number. So instead, let's apply the theorem. How do we do that? A is 5. I is 74. What is M and where does the 21 arise? Well, we are working here in the group Z star 21. The 21 thus arises in our choice of the group G. And the M will be the order of that group. Luckily on the prior slide we saw it was 12. So the solution is let G be the group Z star 21. Let A equal to 5 and M equal 12. Now we can pattern match with this. So 5 to the 74 mod 21 is 5 to the power 74 mod 12, modulo the group order up here. We still have a mod 21 because that's just a result of working in our group G. What is 74 mod 12? Well, 72 is a multiple of 12. So that means the remainder is 2. So we get 5 squared mod 21, 25 mod 21, which is 4. Okay, that should be kind of neat. And here's some few fun things to play with in that regard, where the challenge is don't use a calculator or any electronic tool, but just figure out the values of these expressions using the different number theoretic facts we've studied. Okay. So far we've done math, but now we're turning to algorithms because we, in the software and hardware that implements the crypto, need to implement many of these functions, and we want algorithms for them. So we will have to consider algorithms that for the encryption and decryption are fast. So let's think a little bit about how we measure speed over here. When you take an algorithms class, you often are using the convention that operations on numbers are very fast, a constant time. So adding and multiplying numbers is just a cost that you effectively neglect or push under some big O of 1. But that's only true because usually there you're dealing with small numbers. In cryptography, numbers get ginormous, things of the order 2 to the 512, 2 to the 1024, 2 to the 2048. As a rough analogy, the number of particles in the universe is 2 to the 80. So they're very, very big numbers. When our computer algorithms operate on these numbers, they are provided in binary. So although this is a huge number, 2 to the 2048, it would be provided as a sequence of 2048 bits. And so the algorithm looks at it that way. And the bit length becomes that in terms of which we measure complexity. So remember, in any algorithms course, there's always something called n, right? And you're always talking about order n squared, order n cubed. Well, what is this n? It varies. In a graph problem, it could be the number of nodes in the graph. If you have a matrix problem, maybe it's the dimension of the matrix. So n, when you're dealing with numbers, is the number of bits in the binary encoding of your numbers. So, and that's also sometimes called the length. We might sometimes denote it again by bars around the number. That's not the absolute value for us. It's the number of digits in the bit length. For example, for 7, you return 3 because 7 is 111 in binary and there are 3 digits here. And as usual, running time is measured as a function of the lengths of all the inputs. So with that, let's give here a summary, which is a sheet you might refer to quite a bit in doing things with numbers, which says what are the running times of different operations for algorithms on numbers. So we go right back to middle school math. When you have to add two integers a and b, if you look at the algorithm we learned, you see that it has a running time that's linear in the binary lengths of the numbers, right? You write down the two numbers, one below the other, and then column by column you just add. Multiplication takes quadratic time. So integer multiplication, you remember you have to go through each number, or you have to go through the first number once for every bit or digit in the second number, and that involves a quadratic amount of operations. Integer division, this is a little more tricky to analyze, but it turns out that the algorithm is again quadratic in the number you are dividing and the number you're dividing by. And this is the thing that returns quotient and remainder. Accordingly, mod is also quadratic because it's just the r from here. There's an operation that's quite useful called the extended GCD that we'll see in a bit, and we'll see that it is also a quadratic time algorithm. Now, we saw that in a group like Zn star, every A has an inverse, and we call that the modular inverse to emphasize we're in this group, and there's an algorithm that given A and N returns that value, that unique value. In our prior example, we just kind of did it by hand, but you could use this algorithm, and it also is quadratic. It takes a time which is the length of n, this n over here, squared. One of the most important operations is modular exponentiation. It can take any point in Zn and raise it to an integer power little n, and the algorithm will take big N, little n, and A as inputs and return this value here. Its running time is cubic. It takes a number of operations in Z mod n, which are multiplications, so there's this cost, but the number of times it has to do that is proportional to the binary length of the exponent. And so you get this running time, which in the end ends up being cubic. And this is a central operation for encryption and decryption. More generally, you can talk about exponentiation in an arbitrary group. And that means take a group element and raise it to some power n. And there, the cost is a number of group operations, which is linear in the length, binary length of the exponent. Remember, the exponent is a normal integer. So this just returns as binary length. And group operations are whatever the group says they are. So we don't have to go through all of these, but some of them are kind of interesting. So let's look at extended GCD. This is useful, as we'll see, to compute modular inverses, but also it's a useful cryptanalytic tool. You can often mount attacks using this. So we saw that the GCD of A and N would return the largest common divisor of A and N, call it D. The extended GCD needs to return that, and so it'll return D, which is equal to this. Additionally, however, it will find a way to write that D as a weighted sum or linear combination of the numbers A and N. So it will return weights A prime and N prime, both integers, possibly negative, such that D is this linear combination. Here, oral arithmetic is happening over the integers. For example, what's the extended GCD of 12 and 20? Well, first off, what's their GCD? That's 4, because 4 divides 12, 4 divides 20, and nothing larger than 4 divides both 12 and 20. Now for the weights, our task is to write 4 as 12 times something plus 20 times something. So if we play around, something that works is a -3 here and a 2 here. So let's check. 12 times -3 is -36. And here you have 40. So 40 minus 36, which is indeed 4. So the algorithm will simply find all this stuff for you. Now, we don't have to look at this in great detail, but a quick overview of how it works is that it goes back to Euclid's algorithm for computing the GCD and just kind of embellishes it a bit to also compute these weights. And the main thing it relies on is this fact that allows you to reduce computations of GCD on large numbers to computation of GCD on small ones. So suppose I want to know the GCD of A and N. So what I do now is I divide A by N to get a quotient and remainder. So the remainder is going to be smaller than N, and the quotient will be smaller than A. So the fact is that the GCD of A and N is the same as the GCD of N, the thing you divided by, and this remainder. Okay, again, we're not going to prove that, but let's see how it leads to a GCD algorithm, the natural way to write which is by recursion. So I start with some numbers A and N. I assume they're not 0, or not both 0. The base case is that the number we're dividing by is 0. What is the GCD of some number A and 0? Well, everything divides 0. And the largest thing that divides A is A itself. So the GCD is A. And now I need to write A as something times A plus something times 0. So A is A times 1 plus 0 times 0. So I'm done when N is 0. If N is not 0, I can divide by it. So I divide A by N to get a quotient and remainder. And I know that the GCD of A and N is the same according to this as of N and R. So I recursively call my algorithm on N and R, and it gives me a GCD D. And I can return that same GCD D over here as the one for A and N. But additionally, I have to play around with those weights. This algorithm kindly also gives me weights X and Y. These allow me to write the GCD D as a linear combination of N and R. So Nx plus Yr is equal to D. Okay? But I need to write D as a linear combination of A and N. However, A is a linear combination of Q and R. It's n times Q plus R. If you put all that together and play around with the math, you can see that these weights work, and you can return these. Now the running time analysis is kind of interesting, and you can look in a textbook. I'd recommend Shoup's book for that. But it turns out that you can analyze this to show that the running time is quadratic in the lengths of the two numbers involved. Another fact that's worth knowing from time to time for some usages is that the weights returned are not too large. So in absolute value, they're smaller than the numbers you started with. And this is something we may use at some point. So one of the main applications of extended GCD is to compute mod inverses. So remember, in the group Zn star, since it is a group, any point A in the group has an inverse, A inverse, such that A times A inverse mod n is 1. Since A is in Zn star, it has a GCD of 1 with n. So now we know that this inverse exists, but say I want to compute it given A and n, and say n is quite large, so I don't have time to exhaustively try every candidate in the group as an inverse. So how do I do that? I'm looking for the unique A prime, such that A times A prime is 1 mod n. So here's the trick. Run the extended GCD algorithm on A and n. At first this sounds silly because you would say, I don't need to know the GCD. I already know it's 1. Why am I computing the GCD? Well, I don't care about the GCD, but I do care about the weights. This algorithm will allow me to write the GCD, which I know is 1, as A times A prime plus n times n prime for some A prime and n prime that it tells me. I take this whole equation mod n. What happens? 1 mod n is 1 on this side. Here, this part goes away since it's a multiple of n. And so I get 1 is A times A prime mod n. And that's exactly what I wanted up here. So A prime is the inverse I want. So we encapsulate them now into an algorithm. The modular inverse algorithm takes A and n, runs extended GCD to get the GCD and weights. It doesn't need those two numbers. It just returns A prime modulo n to put it in the right range. In particular, since extended GCD is quadratic time, so is modular inverse. Now, if you want to play around, there's calculators on the internet for all of these kinds of things. So you can take over here, you can take different integers and compute and see about the extended GCD. So let's say we type in 30 and 70 and see what we get. So it says the greatest common divisor is 10, and it tells you the two coefficients to write them in as a 10 is a linear combination of these two. And there's a lot of these calculators. So here, for example, is the multiplicative inverse calculator. So suppose I want the inverse of 7 modulo 12. That should work because 7 and 12 are relatively prime. It'll give me that 7 is its own inverse. It'd be interesting to see what happens if I try 8, because 8 doesn't have an inverse. What will the software do? It'll tell me that there's no modular multiplicative inverse for this integer. And more generally, you can find tons of algorithms out there. So here's modular exponentiation. You can calculate a to the power b mod n. This is the algorithm we're going to study next. So let's do that. When we come to using number theory for cryptography, we'll see that encryption is going to rely on modular exponentiation. So this is an important operation. Most often the group is Zn star for some number n, but we'll study this at least to start with more generally. So we have a group G, some point A in the group, and an exponent which is an integer which we'll assume here is non-negative. And I want to raise a to the power n. Well, I know the definition. A to the power n is a multiplied by itself n times in the group. So there's an obvious algorithm. Start by setting y to the identity element, 1, and then n times just multiply y by a. And are we done? Is this a good algorithm? And the answer is, it is if all you care about is getting the right answer. It gives you that. But it's going to be prohibitively slow for the types of numbers of interest in cryptography. Remember that we're working with numbers that are thousands of bits long, which means the magnitude of the numbers are things like 2 to the power 512. So imagine that this n here was around 2 to the power 512. This is saying I need 2 to the power 512 operations, and there's no way that that's even remotely feasible. If you want to think about it in more theory of algorithms terms, remember that we measure running time as a function of the bit lengths of the numbers involved. So in terms of the bit length of n, an algorithm that has running time proportional to n itself is actually exponential time, because it's 2 to the power of the bit length. So we're looking at exponential time algorithms, and I prefer polynomial time algorithms. So a little bit of thinking, however, shows that we can do much better, because we have a lot of repeated work when we just keep multiplying a by itself over and over again. For example, suppose I needed to compute a to the power 32. Instead of multiplying a by itself 32 times, I can square a, square the result, and keep squaring. So here I have 1, 2, 3, 4, 5 operations, and I've already got to a to the 32. So more generally, if I want to raise a to the power n, the number of I of steps I need is approximately the logarithm of n. Okay, and that's starting to look like polynomial time. So this is good, and this works. The only problem with this is that it assumes that the exponent is a power of 2. If a is not a power of 2, it's not actually clear what to do. So for example, suppose a is 40, n is 40. You want to raise a to the 40. Well, you can go up to here. The next one would be a to the 64 in this chain, and you've gone too far. So maybe you stop here and then start more slowly going to a to the 40. But it's not particularly clear how you do that. And if you just do it by multiplying by a as often as you need, it's actually, again, exponential time. So instead, we'll kind of factor in exactly where you need to get from the beginning by looking at the binary expansion of the exponent. So as an example, suppose that the exponent had binary length 5. So the exponent has the form in binary, this form, or in as an integer, you expand the binary notation. It's this first bit times 2 to the 0, next bit times 2 to the 1, and so forth. Or expand it out more, it looks like this. So we have this as input, and I need to raise a to this power. A is also an input. So here's how I do it. I start with the identity element, or 1. In every step, I square what I had previously, and then I multiply by a raised to the power the next bit position. To start with, that'll be the leftmost bit, b4. What do I get from this? This time I get 1 times a to the b4, which is a to the b4. Notice raising a to the b4 just means I get either a or I get 1, because this is a bit. It's either 1 or 0. Let's repeat that. I square what was here and then multiply by a to the b3. So I get a to the twice b4 plus b3. Repeating, this is multiplied by 2 in the exponent. So 4b4 plus 2b3, and I bring in the next b over here. And so now you see what's happening. This will slowly grow until it's the binary expansion of the exponent. or it's rather the integer expansion of the exponent, and you have n sitting here, and that's it. So you're done. Let's encapsulate that into code. Let this function binary take a number n and return its binary exponent. So in other words, n is this sum. The exponentiation algorithm in group G takes a group element a and an integer n. It first computes the binary expansion of the exponent, and then it does what we said on the prior slide. You start by initializing y to the identity element of the group, and then you go from the most significant bit down to the least significant, and each time you take your current y value, square it, multiply by a raised to the power of the current bit in the binary expansion of the exponent, and that's your new y value. And that, when you return that, you in the end have a to the power n. Good, so we've now succeeded in doing this quickly, and it has a running time which is linear in the length of the exponent. In other words, in k over here. And each step in the loop is a constant number of group operations. So either 1 or 2, 1 for the squaring, 1 for the multiply if the bit is a 1, otherwise there's nothing needed. So in particular now when we write mod exp, we mean this, but in the specific group Zn star or Zn. So we have the group element A, we have n, the exponent, and we have this number which effectively is defining the group we're working in. And so it'll return a to the power little n mod n. And its time will be this many group operations, but the group operation is multiplication mod n, and remember multiplication mod n is quadratic. So each group operation costs this much. And so the takeaway is that this is cubic time, and cubic time is quite a bit. So we'll see that this is considered slow, and it's one of the things that makes public key cryptography a bit slower than one would like. So people spend a lot of time optimizing this and improving it with better implementations and better algorithms and so forth. So here we have a computational problem which is actually in that vein. What it's doing is it's saying, if I have to figure out a product of the form a to the x, b to the y mod n, there's something better I can do than the naive algorithm of just raising a to the x, b to the y, and multiplying them. Effectively, the cost of this is pretty much just the cost of a single exponentiation. So that's as much as we'll do as far as giving details of these algorithms. And so here is just the summary chart again, so you have a reference point. All right, so what we've done now is we've developed number theory and algorithms on numbers, but we haven't yet done any cryptography. What's needed to do some cryptography is something which we would call a computationally hard problem. It means I need something where I expect adversaries will have a hard time doing it, some computational task, because then I want to set things up so that breaking my crypto forces the adversary to perform this task. And indeed, the neat thing about number theory is that there are examples of these kinds of problems. The one we'll see here is going to be the discrete log problem. So in order to get there, though, we need a little bit more number theory. Now, again, you may be, feel you're inundated with number theory, but actually it's quite surprising and interesting that you need very little number theory in order to get enough to do non-trivial crypto. Just something from the first few weeks of a undergrad algebra course is enough. So with that as motivation, here's a definition, again, common in group theory. If I have a group G, it has some operation. Consider a subset of the points in the group. Some of those subsets are special, and I call them subgroups. That happens if when I look at that subset and I look at it under the same operation as it inherited from the overlying group, it itself is a group, meaning it satisfies all the 4 properties. So as an example, we know that Z star 11 is a group under multiplication mod 11. And here's a subset of it, 1, 2, 3. All of these are points in here. And is it a subgroup? Well, you see immediately it's not. Why is that? It fails, for example, closure. Take 2 times 3, it's 6 mod 11. But 6 is not in the set. And for S to be a subgroup, it would need to be in the set. It also fails other properties. So the identity element is fine, it's a 1, but the inverse of anything in the group ought to be in the group. What's the inverse of 3? Well, the inverse of 3 mod 11 is 4, because 4 times 3 is 12, which is 1 mod 11. But 4 is not in the group, so we violated that property as well. However, here's another possible set, 1, 3, 4, 5, 9. You can check that this actually is a subgroup. As a bit of spot checking, multiply 2 things in here, 3 and 5. 5 times 3 is 15, mod 11 is 4, but 4 is in here. What's the inverse of 4? Well, it's 3, and 3 is in here. Okay, so we know now what subgroups are. There's a simple way to check if something is a subgroup, and that happens if your set is non-empty, and whenever you take 2 points in it and you operate with the operation of the overlying group G to compute XY inverse, it'll also be back in the set. So that should alleviate some of the burden of checking something is a subgroup. Now there's some specific types of subgroups that we're interested in. So let's again let G be our group. Let's M be the integer that's the order of the group. Remember, that's simply its size, the number of elements in the group. And let G be a particular point in the group. And let's start raising G to powers. So I collect here G to the 0, G to the 1, G to the 2, and so forth. And I stop at M minus 1. Remember, M is the group order. That's some set. And I claim that this set is actually a subgroup of G. We don't need to prove that, but as per the subgroup definition in the prior slide, it satisfies all the group axioms. Okay, now consider the size of this set. How many points are in there? Naively, you may think, oh, there's going to be m points in there. Why? Because there are m choices for the exponent I, according to this. But those choices may not all yield distinct values for g to the I. Some of those g to the i's could be the same. So the fact is that the size of this set could be smaller than the group order. Now, given that this is a subgroup, there's a fact of group theory that says that the order of the subgroup always divides the order of the group. And so it turns out that whatever this number is, it's a divisor of the group order M. We sometimes call the size of this set the order of G itself. So far we've defined the order of a group. Now we're defining the order of a group element. And this is one definition. An equivalent way to think about it is the order of G is the smallest power to which I need to raise G to get back the identity element. This is the smallest positive power, right, beyond 0. Okay, now as we said, this set is either of size m or possibly smaller. The case where it is of size m is interesting because when that happens, it means that this set equals the entire group. So the set of powers of G recovers everything in the whole group. If that's the case, we like G and we call it a generator or sometimes a primitive element. Another way of putting it, the order of G is the same as the order of the group. It is M. All right. Now, if you look at a particular group, you can ask for every point in the group, is that point a generator or not? Maybe it is, maybe it isn't, and we'll figure out how to determine that. But sometimes the group has no generators, and sometimes it has some. We like the groups where there exists a generator, and we call such groups cyclic. It doesn't have to be the case, nor can it be the case that everything is a generator, but as long as one exists, we call the group cyclic. Okay, so we now have these concepts: generators, cyclic groups. We have ideas about raising to powers and subgroups generated by an element, and so forth. So let's play around with this a little bit numerically before going on to discrete logs. So consider the group of integers mod 11. 11 is a nice number to use here because the group has size 10. So the number of points in it is the fingers on our hands. And this is a kind of novel set of properties about them than we might have usually considered. So the operation is multiplication mod 11, but the order of the group is 10. So let's take the number 2, which is in the group, and start raising it to powers. What powers? Just all of them. Start from 0 and keep going. Okay, 2 to the power 0 is 1, 2 to the power 1 is 2, 2 squared is 4, 2 cubed is 8. Now 2 to the 4 is 16, and 16 mod 11 is 5. Okay, I need to keep going like that. It's getting a bit tedious to raise 2 to the power 5, try to do it mod 11. So we see that there's a simple trick. When I want to move to the next cell, I just have to take the previous cell, multiply by 2, and do it mod 11. So from here to here, 5 times 2 is 10. From here to here, 10 times 2 is 20, 20 mod 11 is 9. 9 times 2 is 18, 18 mod 11 is 7, and so on. When I get here, I notice I hit a 1. I expect that because remember, raising to the power of the order of the group is always going to get you back the identity element. Okay. Having done it with 2, I also do it with 5. Raise 5 to all powers. Here, the trick is every time you move from one cell to the next, you multiply by 5 and do it mod 11. So 5 to the power 0 is 1. Multiply by 5, you get 5. Then 5 times 5 is 25. Mod 11 is 3 because 22 is a multiple of 11. 5 times 3 is 15. Mod 11 is 4, and so forth. So remember, we had this set of all the powers of a group element that we denote like this. So what is the set corresponding to 2? It's simply everything that you see in this row, every distinct thing you see in this row. Now we write them down, but we reorder them. We notice that we have 1, 2, 3, 4, 5, 6, 7, and so forth. And so we get this list actually of all the numbers between 1 and 10. Let's try it with 5. So the set generated by 5 is everything in this row. We collect up everything there. We have 1, 3, 4, 5, 9. But that's it. Here we just have those same things repeated. So we have a smaller set. So we see that the sizes of these sets vary. We can check, however, that these sizes always divide the group order. Here it's 10, which divides 10. Here it's 5 that divides 10. If this had come out to be a set of size 6, you know that you did something wrong numerically. According to our definitions, 2 is a generator of the group. Why? Because this set is all of z star 11. 5 is not a generator because that set is not all of z star 11. The group z star 11 is cyclic because I found one example of a generator. I don't care that this one wasn't. So a simple exercise where you can play around with this for some other groups. We can now come, and indeed interesting how quickly that was actually, to the definition of this function of interest for cryptography, which is the discrete logarithm. So we fix some cyclic group and we let G be a generator of the group. What does that mean? It means that every point A in the group can be written as a power of G. It's G to the power I for some I, And if we confine I to the range 0 through m minus 1, it will be unique. Hence, we can see that I with the g fixed as a function of a, and we call that the discrete log of a. So the discrete log with the group and generator fixed of a is the unique integer I, such that raising g to the ith power gives you back a. Another way to think about it is that the discrete log function is the inverse of the exponentiation function. So if I take g and raise it to the power I to get a group element, and then take the discrete log, I will just get back I. Similarly, if I raise g to the power the discrete log of a, then I will get back from this an I such that g to the I is a, and so this returns a. Okay, so in this sense, the two functions reverse each other. So let's see if we can compute some discrete logs. Well, again, we work with our group Z star 11 as an example. It's a cyclic group of order n, 10, and we know that 2 is a generator. So what is the discrete log in this group? Base 2 of some point a in the group. It's whatever index I has the property that 2 to the power I is a in the group. Here, that means 2 to the power I mod 11. Now here may be worth clarifying something that sometimes gets confusing. What are these mods coming from relative to the prior slide where there were no mods? They come about because the prior slide gave definitions in an arbitrary group. Here we have a specific group, Z star 11, and the group operation here involves the mod. And this operation was just hidden in the general group operation earlier. Okay, the range for the exponent is Z10. It's the order of the group, 0 through 1 less than the order of the group. Okay, remember that we did write a table where we raised 2 to all possible powers in the group. So here I've just repeated that table, showing 2 raised to all powers, up stopping at 9. There's no point going to 10 because you just get back 1. How do we then compute discrete logs? Discrete logs apply to group elements. So I would need to look at these numbers 1 through 10, and they return integers, and they need to return integers I, such that 2 to the power I is whatever a is returned here. So here I know I should get a 0 because 2 to the power 0 is 1. But how do we get these? Well, the simple observation, which was embedded in the prior slide in saying that the discrete log and exponentiation functions are inverses of each other, is to just read this table backwards. So if I want the discrete log of 1, I find 1 here and see what's above it. Discrete log of 2, find 2 here, see what's above it. 3, find 3 here, see what's above it. And in that way, I can fill in this table. Okay. So we have, at least in principle and mathematically, a nice simple way to compute discrete logs. Okay, so here's a little exercise where you play around with stuff like that. Now, we've talked about these cyclic groups kind of in the abstract, and we saw that Z star 11 was cyclic. But for cryptography, we're going to need very, very big groups of this type. So we would be interested in how we find groups like this. It turns out that the fact that Z star 11 was cyclic isn't a coincidence, in the sense that whenever you take the integers mod of prime and relatively prime to that, you get a cyclic group. So for any choice of a prime p, the group is cyclic. That's a fact. Here's another fact. Take any group and look at what its order is. If that order is itself a prime number, you're guaranteed the group is cyclic. This, by the way, is very easy to prove. This takes more work. Sometimes the two get confused because someone might think that this fact implies this one. Remember that the order of Zp star is not p, it's p minus 1. There's p minus 1 points in the group. And p minus 1 is not prime. In particular, p is typically odd, and so p minus 1 is always divisible by 2. So both these facts are important in that, and they're distinct from each other. Finally, if you have a finite field and you look at its non-zero elements, it turns out it's a cyclic group under the multiplication operation of the field. Okay, now we've seen algorithms for lots of number theoretic functions. Extended GCD had a nice quadratic triangle algorithm. We were able to do exponentiation. We were able to do modular multiplication. So now let's look for an algorithm for the discrete log function. I want a fast way to compute the discrete log of any given number, having fixed the cyclic group and knowing its order and knowing a generator of the group relative to which we are defining that algorithm. What's the first thing you might do if you see a problem like this? Let's go see if there's anything on the internet that solves it. Well, there's lots of number theoretic functions. And here's a discrete log calculator. So I could give it a base, maybe 2, a modulus, maybe 11, and a power, maybe 5. Wait. So what it's saying now is, what is the discrete logarithm of 5 to base 2 in the group? And it's saying it's 4 plus any multiple of 10, but if you're in the range we're thinking of, doesn't matter. And why is that? Because 2 to the 4 should be 5 mod 11, which you could check by a modular exponentiation operation. Okay, so nice, we can compute discrete logarithms. However, I wonder what would happen if we started putting in rather big numbers over here. Oh, maybe that didn't. I have to also assure that 2 is actually a generator. I guess it wasn't back then. But what you should see happen is that the algorithm will start failing after a while. Why? Well, that's what we're kind of going to see here. So, so let's go back to our task. I want an algorithm to compute discrete logs of some point big X in a group G relative to base little g. So I'm looking for an exponent, which is an integer, such that g to the little x is big X. Again, this is in our abstract group. If you were working in the group of integers mod something, this is g to the little x modulo whatever that is. But there's a simple way to find it, because we know that this little x falls in a specific range, which is 0 through m minus 1. So I can just try every little x in that range, raise g to the power little x with my mod x algorithm, and check if I get back big X. I know that this computation is efficient, so this step in the loop wouldn't take too long. Does this work? It does, if you think of working as being finding the right answer, but it's going to be slow. Again, why is that? Because our groups are enormous. M could be of the order of 2 to the 1024, and there's no way that many operations are a reasonable thing to do. Again, this is an exponential time algorithm measured in terms of the bit lengths of the quantities involved. So it's going to be prohibitively expensive. Okay, so where does that leave us? Well, remember that we saw the same thing with modular exponentiation. The first algorithm we wrote down was exponential time, but then we said, oh, okay, let's look at it a little more carefully. Here's some insight, here's a trick, and suddenly we have a much, much faster algorithm. Can we do that with discrete logs? And the answer is no. Now, you can get algorithms significantly better than the naive one we wrote on the last slide. But what you can't get is a polynomial time algorithm, meaning one that's kind of like exponentiation and allows you to compute this discrete log on extremely big numbers in reasonable time. So what people do is they search for the best possible algorithms, And this represents the state of the art. It turns out that what's the best possible algorithm does depend on the choice of group. If you're working in the group of integers, mod, or prime, then the best algorithm has this running time. So what is this formula? E here is the base of the natural log, so 2.7. And you raise e to this power. A constant, p is the number here, modulo which you're working. You take its natural log and then take the cube root. Take its natural log twice raised to the 2/3 power. All that in the exponent with e as the base. There's some caveats. It's actually a little bit less because it's not really p that's here. It's the number q, which is the largest prime factor of the group order. But if p is properly chosen, q is very close to p. If you're in an elliptic curve group, the group of points over an elliptic curve, the running time is about square root of p. To compare these, write square root of p as e to the power half of the natural log of p. And you see that this is much bigger than this in the exponent. So this is a much slower algorithm. Okay, so, but this is just a complex formula. What does it actually mean in terms of how fast these algorithms run? Well, you can try to play with that by plugging in numbers, but the real test is to implement these things and see what the running times are. The way that works itself out is that people try to find discrete logs relative to larger and larger primes. And you seek records. How big a prime can we find discrete logs relative to? And as implementations and algorithms improve, you see progress. So in 2005, they were able to find discrete logs relative to a 431-bit prime. It went up to 530 a few years later, sometime later to 596. This was a big step because 512 bits was considered like something at the point where it should be secure, and this showed that it wasn't. And a couple of years back, they even managed to compute a discrete log boundary of 795-bit prime. With elliptic curves, since that formula is much bigger, the algorithms are slower. And it appears that right now, groups of size about 2 to the 114 are where as much as these algorithms can handle. There's more details of this, if you like, on the internet. There's, for example, this is a Wikipedia page devoted to discrete logarithm records. They cover the different groups, integers, mod p, the finite field group, elliptic curve groups, and they tell you. So on December 19th, the team that included Nadia Henninger discovered the last discrete log we talked about, and here are some prior ones. And they tell you what kind of computation is involved. So you can see here what algorithm was used, the number field sieve, the discrete log took this many core years, and so forth. And then for elliptic curves, they discuss how Certicom Corporation has issued a bunch of challenges and what progress is being made on those, and then also other general computation records. So now, potentially in the future, better algorithms will emerge. There's nothing to indicate that the algorithms we saw are the best ones. It's just the best ones we know. But right now, that being the state of the art, we are willing to conjecture that those algorithms are the best ones and build crypto based on that. Effectively, what this shows is that if you pick the P large enough, for example, 2048 bits long, there is no reasonable way to compute discrete logs. Nonetheless, the operations like exponentiation are quite fast. And that gap is where we can fit cryptography in. So nowadays, things are moving more and more to elliptic curve groups. And why is that? Well, the reason is that you get the same security with better performance. How does that work out? Suppose you have a target like 80 bits of security. That means I want the time to compute a discrete log to be about 2 to the 80. So now, how large do I have to pick p so that in zp star, the time to compute the discrete log is about 2 to the 80? Well, I would need this formula to come out to about 2 to the 80. If you play around with that, taking into account constants and implementation, it turns out p is about 2 to the 1024. If I want to work in an elliptic curve group with prime order p, and I want the computation of discrete logs in that group to take time 2 to the 80, well, I know that the best algorithm will take time square root of p. So I'm looking for when is the square root of p approximately 2 to the 80, and the answer is when p is about 2 to the 160. So this means that this group has a much smaller size than this one. How does that play out? Well, the difference in group sizes shows up in the cost of modular exponentiation, because remember that was cubic in the representation size of a group element. So if you look at the ratio of costs, it's the ratio of these exponents raised to the third power. And so, in fact, an exponentiation costs 260 times more in this group. And so you have a simple reason why people prefer elliptic curve groups. So far we've studied the discrete log problem informally, but in order to build on it and to be able to use it as a basis for theorems in cryptography of the form, if the discrete log problem is hard, my scheme is secure, we need to formalize it. So we turn this into games and so forth in the following way. So let's fix our group, fix a generator of the group. It's a cyclic group, and we fix its order m, and we let A be an adversary. Now, informally, we had talked about computing discrete logs for any provided point in the group. What the game does is it's specific about how those points are chosen. It says they need to be random group elements. So what initialize does is it creates a random group element. How does it do that? It picks a random exponent, little x, in the correct range, which is 0 through 1 less than the group order, raises g to that power, and gets a group element, and returns that. That's the challenge for the adversary, and its job is to find its discrete log, which is simply little x. So it turns it along, and eventually it outputs and takes that, and it checks, is it the correct discrete log of big X, meaning does it equal little x? If so, it returns true, else false. And so our adversary has a certain advantage, which is the property that when executed in this game, the game returns true. And we denote that like this, DL for the discrete log problem. The discrete log problem is with the group and generator fixed. So they appear over here, and then the advantage is for this adversary. Now, yet another reminder, if you look at this in a concrete group, like integers mod n, you see mod n's appearing everywhere. Well, not everywhere, but where? Here, this will be g to the x mod n. Okay, but that is understood because here we are talking about group operations in our abstract group G. So now it would be nice if we could see the discrete log problem as the source of security in the Diffie-Hellman key exchange. But it turns out that there we need a slight variant of it called the computational Diffie-Hellman problem. Again, there's a group G which is cyclic, and we fix a generator of it, and we let little m be the group order. The computational Diffie-Hellman problem says I give you as input not one group element, but two of them, big X and big Y. Given that G is a generator, we know mathematically that big X is G to the little x for some little x, correspondingly for big Y, where these numbers are in the usual range, Z sub the group order. The output then is to determine G raised to the power the product of those two exponents. Okay. So that's it. That's our computational problem. It underlies the Diffie-Hellman secret key exchange. And so it's of interest to see, can we solve this? How how hard is it in terms of designing algorithms? How fast would the algorithms run? One thing we may notice is that if I can compute discrete logs, it's easy to solve the CDH problem. Why is that? Given big X and big Y, I perform a discrete log computation to get this exponent little x. Once I have that, I take big Y and raise it to the power little x. And that gives me g to the power little x little y. So what this tells us is that solving discrete logs allows you to solve CDH. Now, maybe there are other approaches to solving CDH, but the fact is that mostly we don't seem to have discovered any. This approach is kind of the best we've been able to think of. And the result is, given that the discrete log problem is hard, or at least can be hard through appropriate choices of the group, we are willing to assume that the computational Diffie-Hellman problem is also hard. Now, technically, these two problems are not equivalent. Potentially, there is a way to solve computational Diffie-Hellman that avoids computing discrete logarithms. But at the moment, no such method is actually known. So here we formalized the computational Diffie-Hellman problem through a game, just like we did for discrete log. We fixed our group of order m, and what the game does is an initialize. It picks two random group elements. Again, the way it does this is it actually picks at random exponents in the range z sub m, and then raises g to the respective powers to get the group elements big X and big Y. What it returns and is provided to the adversary are the two group elements. The adversary's job is to trundle along and return group element z to the game. Finalize takes that, and to see if the adversary wins, it compares it with g to the power little x little y. It can compute the latter because it knows x and y. And if that returns true, the adversary wins, and the adversary has some advantage, which we call its CDH advantage, relative to this fixed group and generator.